Victorian Network. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we will consider the application of Laplace transform in the transient analysis, and it contains the transient analysis method, step response of RL, RC and RLC circuit, and the examples. In the last video, we have considered the transient analysis, and it has two different approaches. One is the classical approach and another one is the Laplace transform approach. So, in the last videos, we have considered the classical approach, and here we will consider the Laplace transform approach. So, a circuit having the constant source, and if the current and voltage does not change with the time, then the circuit is in the steady state. And if due to change in the excitation of the current or voltage changes from one state to other state, then the circuit is known as in the transient state. The time taken for the circuit to change from one state to another state is known as the transient time. So, the overall response of a system is divided into two parts. One is the transient response or the natural response. Another is the forced response or the steady state response. So, in this video, we will consider the Laplace transform approach of this transient analysis. So, first consider a step response of a RL series circuit. Now, the current through a linear inductor must be continuous, because L into di dt, that is equal to voltage across the inductor, and it is not proportional to the current flowing through it, but the rate of the change of the current with respect to time. Now, when the current is constant, then the voltage across the inductor is 0, because under steady state the DC current inductor acts as the short circuit, and AC is constantly changing, and hence the inductor will create an opposition of voltage polarity that tends to limit the changing current. If the current changes rapidly with time, then the inductor causes a large opposition voltage across its terminals. And if current changes through inductor from one level to other instantaneously, then the voltage across it becomes infinite, which is required in infinite power. So, instantaneous changes in current is not possible through an inductor practically. So, here we are considering a series RL circuit, and we are considering that initially this RL circuit is de-energized, and the V is the constant voltage source, and at t is equal to 0, the switch is closed, and when the switch is closed, voltage supply is connected to this RL circuit. So, the governing equation can be written as V into ut, because we are considering the unit step function, and minus RIT minus L di dt is equal to 0, and the voltage exists only when the switch is closed, and the voltage is V into ut, that is the unit step function. So, now we can take the Laplace transform in both sides. So, it becomes V by S, because for the step function the Laplace transform is 1 by S. So, this V by S equal to RIS plus LSIS minus I of 0, and I0 is the initial value of the current, and it is to be considered here as 0, because the circuit has been assumed to be in the de-energized condition. So, we can write the equation V by S equal to RS plus LSIS. So, we can take IS common in right hand side, then it becomes R plus LS, or from this equation we can find out IS equal to V by L by R plus LS, or it can be written as V by L divided by S into R by L plus S. So, using partial fraction, we can write this IS is equal to A by S plus B by R by L plus S. So by solving using the partial fraction, a is v by r and b is equal to minus v by r. By putting the values in this equation 3, we can write this is equal to v by r by s minus v by r by l plus s, or it can be written as v by r into 1 by s minus 1 by r by l plus s. So we can again take the inverse Laplace transform, and the it becomes v by r into 1 minus e to the power minus r by l into t. And in this section, this v by r is a steady part, and v by r into e to the power minus r by l into t, that is the transient part of the system. So using this Laplace transform, we can say that the equation of the it remains same what we achieved in the classical transform, classical approach. So this is the step response of the RL circuit. Next, we are considering that the RC circuit. So here the capacitance of the circuit is initially having charge, that is the Q0, and it due to this flow of some previously applied current, and the switch is closed at t is equal to 0. So the governing equation becomes v is equal to v into ut, because we are actually applying the unit step voltage. So v into ut equal to rit plus 1 by c it dt. And using the Laplace transform, we can say v by s equal to r into is plus 1 by sc and is minus I0. Now I0 is equal to actually Q0. So we can check it in the left hand side. So v by s minus Q0 by cs, that is equal to is into r plus 1 by cs. Or from this we can find out the current equation, that is is equal to this v by s minus Q0 by cs by r plus 1 by cs, and after solving this we can find out the constant value c divided into 1 by s plus 1 by rc. And taking the inverse Laplace transform, we can write this it becomes c into e to the power minus t divided by rc. So this is the step response of a RC circuit, and this is the current equation, the current flowing through the circuit. Now this is the step response of series RLC circuit. Here the switch is closed at t is equal to 0 seconds, and then it is connected to the voltage supply is connected to the R, L and C, and we are assumed that all initial conditions are 0. And when the all initial conditions are 0, then if we apply KVL, then we can say v into ut equal to rit plus L dr dt plus 1 by c I dt is equal to ut, and all the initial current initial conditions are 0. So initial inductor current is also 0, and initial capacitor voltage is also 0. By taking the Laplace transform, we can say it becomes 1 by s equal to ris plus 1 by sc into is plus ls is, and that is equal to is into r plus ls plus 1 by cs. From this equation, we can find out the equation of is, and that is equal to 1 by l divided by s plus alpha into s plus beta, where the alpha and beta are the two roots of this second order equation, s square plus r by ls plus 1 by lc. So applying the Sridhar-Acharya formula, we can find out the values of alpha and beta, and this alpha beta is equal to minus r by 12 plus minus root over of r by 12 whole square minus 1 by lc. So here there will be three possible solution of is depending upon the values of this r by 12 whole square minus 1 by lc. So for the case 1, we are considering that the value of this r by 12 whole square is greater than 1 by lc, and if it is so, then the alpha beta value is real and the unequal. So we can write is is equal to k1 by s plus alpha plus k2 divided by s plus beta. So applying the partial fraction, we can find out the value of k1 and k2 like this: 1 by alpha divided by minus of alpha plus beta and K2 is 1 by L divided by alpha minus beta. So the IT becomes the Laplace inverse of this equation, putting the value of K1 and K2. So IT becomes e to the power minus alpha t by L into beta minus alpha plus e to the power minus beta divided by alpha minus beta. And for the next case, we are considering that R by 12 whole square is less than 1 by LC. And here the alpha and beta becomes a complex conjugate. So we are considering that A is equal to A plus J beta, whereas beta and beta is equal to A minus J beta. So IS becomes the K1 by S plus alpha, alpha means A plus J beta, whereas K2 by S plus beta, that is equal to A minus J beta. So solving this equation, we can find out the value of K1 and K2 like this, minus 1 by J into 2L beta B, and K2 is equal to 1 by J into 2L into B. So putting the values of K1 and K2, the IS becomes this one, 1 by J into 2L into B by S plus A plus JB plus 1 by J 2LB by S plus A minus JB. So taking the inverse Laplace transform, we can find out the equation of I is e to the power minus kt by LB into sin dt. And for the third case, where the R by 12 whole square is equal to 1 by LC, that means alpha and beta is equal to equal, and we are considering that alpha equal to beta, that is equal to k, then IS is equal to 1 by L into S plus k whole square. From this equation, taking the Laplace inverse of this, we can find out that IT is equal to 1 by L into t into e to the power minus kt. So for the different values of the R by 2L and 1 by L e to the power of LC, we are finding out the three different type of response of this RLC series circuit. Next, take an example, and here we need to find out the complete expression of current after closing the switch when the battery voltage 10 volts is applied for a steady state period. And the battery voltage is 10 volts, R1 is 1 ohm, R2 is 2 ohm, and the inductor value is 1 Henry. So when we are applying the KVL, we can write down the EUT equal to RIT plus LDIDT. And we are considering that switch is closed. So taking the Laplace transform, it can be written as E by S equal to R1 into IS plus L into SIS minus I0. When the switch is closed, this resistor is not working. So from this equation, IS is equal to E by L plus SI0 by S into R1 by L plus S. So using partial fraction, we can find out the value of A and B, and A is E by R1, that is equal to 10 volt, because E is given as the 10 and R1 is 1 ohm, and B is equal to minus E by R1 plus I0. So just before the switching, the total current, that was actually the initial current, that is equal to 10 divided by this R1 plus R2, that is 10 divided by 3, so it becomes 2.60 amperes, and the value of B becomes minus 10, because minus of E by R1 is minus 10, and I0 becomes 2.60, so it is the minus 6.67 ampere, and the IS is equal to 10 by S minus this one. So IT is the 10, taking the inverse Laplace transform from this equation, that is equal to 10 minus 6.67 into 1 by 1 plus S. The inverse Laplace of 1 by 1 plus S is equal to e to the power minus t. So the overall current expression is 10 minus 6.67 into e to the power minus t ampere. Let's take another example. Here in a series RC circuit, for a step input voltage, we need to find out the initial current at t is equal to 0 plus, following the switching on at t is equal to 0, and assuming the initial charge of the capacitor is Q. So for the step input voltage V, the current in the RC circuit is IS equal to V minus Q0 by C divided by R into 1 by S plus 1 1 by RC. And if we apply the initial value theorem, and the initial value theorem is f of 0 plus, that is equal to limit s tends to infinite s of fs. So if we apply this initial value theorem, then we are finding out that I0 plus is equal to b minus q0 by c divided by r. And for the next example, a given circuit, for this given circuit, the current, we need to find out the current to the capacitor at t is equal to 0 plus, and following the switching at t is equal to 0. And we are assuming that capacitor to be initially charged, and the values are given. C is equal to 100 microfarad, J is equal to 10, and the capacitor is initially at discharge condition. So if we apply KVL, the network equation becomes G equal to RIT plus 1 by C IT dt. So applying the Laplace transform, we are getting that V by S is equal to R divided by S and plus 1 by SC into IS. Here I have omitted the I0 part because in the equation, in the problem, it is given that the circuit is initially discharge condition. So we can assume that the initial current is also 0, and taking from this equation we can find out the value of Is, and Is is d by R divided by S plus 1 by RC. So taking the inverse Laplace, It becomes V divided by R and e to the power minus C divided by RC. So putting the value V is equal to 10 and R equal to 2, V by R becomes 5 into e to the power minus C divided by R into C. So the capacitor value is 100 microfarad and R is 2 ohms. So it becomes 200 into 10 to the power minus 6. So I of 0 becomes on this is the initial part, that is I of 0 equal to 5 ampere. So in this way, without using the classical method, by using the Laplace transform, we can find out the transient response of the circuit. So these are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.